All right. Next up, we have Mike Meehan. I Googled Mike in order to prep an introduction to his talk, and unfortunately, I think that all of the people that came up may have been slightly different Michael Meehan. So I apologize for that.
My advisor would be displeased. We just redid our website.
Oh, I probably
I'm just kidding.
misspelled it.
I'm
That
just
might
kidding.
be it.
No, it's okay.
So thank you, and please take it away.
So yeah, my talk is going to be completely different than anything else that I've seen, and I'm part of the 25% that is other as far as astronomy goes. So today I'm going to be talking about some of the simulations that we do on buoyant plumes. So I'm Mike, my PhD advisor is Peter, and so on the right here, I have an example of from a simulation that we're currently doing where we're injecting helium into ambient air. And you can see we inject at a very slow velocity, and then buoyancy takes over and dominates the dynamics downstream. And so we see these kinds of applications in many, many different realms of the world. So in in the geothermal context, we see volcanoes, where volcanoes are expelling hot gases, and this accelerates upwards due to buoyancy, or hydrothermal vents, where deep sea magma heats up the cool ocean water, and then it's expelled through these crevices. Yeah, and popular topic today is disease transmission. You see this whenever someone breathes out and produces like a cloud of hot gases. And after this cloud initially is injected, eventually buoyancy takes over because hot gases rise, and this gets into the ventilation system, promotes transport of disease transmission. More what we're focusing on in our lab is engineering applications. So on the left here, I have a image from the 1960s of a test facility for rockets, and you can, at very close to the Earth, you can see very, very fast gases coming out, but eventually these become buoyancy dominated downstream. At a much smaller scale, we are looking at industrial burners. So these are generally used for heat treatment processes, but very much smaller scales. And then what we are primarily focused on, like the most application based, is pool fires. Pool fires are pretty common in chemical plants, forest fires, something along these lines. And all they are is simply, if you can imagine a liquid or a solid burning. And so there's very, very low initial momentum at the surface here. But then as the reactions occur, then the gases become hot and buoyancy dominates. And what we found is that actually the dynamics in something like this, being primarily buoyancy dominated, are much easier to understand in a simplified case without reactions. So just injecting helium. And so actually on the right here, there's a test case at Sandia National Laboratories where they inject helium through this tunnel. So what our goal is to basically understand how fluid dynamics impacts these highly buoyant non-reacting plumes play a role in the reacting equivalent. To do so, we're looking at a very, very simplified configuration where we are injecting helium axisymmetrically into the bottom of the domain. We're doing so with high fidelity simulations. So whenever I say high fidelity simulations, it's like a coarse direct numerical simulation or an implicit LES simulation. There's no subgrid scale filter for these types of flows. And we're using PaleALM, which is a low Mach combustion code built on AMREX, and low Mach meaning that there's variable density, but the scales that we're looking at as far as the velocity goes is not compressible. So we don't need to resolve like an acoustic time scale or anything. And so through these simulations, we want to address a number of different questions. A few of these being how the Reynolds number impacts some of the structure and dynamics and puffing frequency. I'll talk about this puffing frequency a bit more later in the visualizations. But most studies in the realm of pool fires or buoyant plumes discusses Richardson numbers, which is just a ratio of buoyancy flux to inertial fluxes. But we're looking at the Reynolds number, and as you guys might imagine, that this is important for how turbulent the flow is. The other things that we're going to look at is being able to predict near field fluxes. So fluxes are extremely important in theoretical modeling of buoyant plumes, jets and plumes. And so we want to be able to predict properties of the flow in the near field. We already know how to do it in the far field. We want to do it in the near field. And then lastly, we want to look at how vorticity is produced, transported, and dissipated. And as you'll see, vortex dynamics play a huge role in these flows. And obviously don't have enough time to actually address these questions fully, but I'm just going to highlight some of the things, particularly that we're using with YT and how it makes our lives so much easier. So simulations, PaleoLM, block structured adaptive mesh refinement code. It's built on Amrex. So these are essential because we need to resolve very, very small scale features, but we need a very large domain to have the proper entrainment patterns in the flow. And so what this looks like, as most everyone here I think uses adaptive mesh refinement, but if I have some sort of variable in the flow field that I want to refine on, the simulation adaptively refines it in a nested grid style. So what we're doing for our simulations is refining on cell-to-cell variations in the density as well as vorticity magnitude. So what this may look like is if you're injecting helium at the bottom of the domain here, gravity pointing downwards, you get these coherent structures here. And then at the interface where the helium and the air are interacting, we're refining, and where vorticity is large. And so actually we do a lot of the analyses that we have done in the past relied on uniform grids. And then whenever we finally said we need AMR to actually do this stuff, we had major issues figuring out how to even deal with the data sets. And so YT was our solution. It gives us such a versatile repertoire of methods to extract data, as everyone here knows. Quickly, an overview of the simulations that I'm looking at in particular. We're injecting helium at the bottom of the domain, and then in an isothermal condition, quiescent air up here, and the computational domain to give you a sense of what we're looking at is a meter cubed, quarter meter diameter that we're injecting with 2 levels of adaptive mesh refinement. Non-dimensional parameters that we're looking at are Reynolds numbers between 200 and 2000, and then Richardson numbers between 4 and 126. The Struhel number down here is a measure of puffing frequency, like a non-dimensional puffing frequency that I'll discuss a bit more later. To give you a sense of the qualitative plume dynamics that we're looking at, on the left here, I have the lowest Reynolds number case for a Richardson number of 40. And then on the right, I have the highest Reynolds number of 2000. You can just see qualitatively how much different the near field is between these simulations. On the left, it's much more laminar. On the right, it's much, much more turbulent. But a very particular interesting phenomenon occurs as you increase Reynolds number from about 200 up to 2000, which I'll show on the next slide. If I look at cross sections in the plane at a quarter diameter downstream and a half diameter downstream, you can see on the left here that the oscillations are very, very axisymmetric. They're very circular. But on the right, you can see these structures forming. We call them finger-like structures, where the helium is protruding out radially. And so as you increase Reynolds number, these structures are forming at lower streamwise locations, and they're also much smaller in scale. You can see just along the interface on some of these puffs that the small scale structure. And this is really important. This was a visualization that my lab mate did in a few years ago with YT. These structures you can see in 3 dimensions much more clearly. These are essential, as the community puts it, to resolving for accurately modeling buoyancy-driven flow. So if you don't get these finger-like structures in a very turbulent condition, then you don't predict the correct statistics in the flow. And on the right here, I'm just showing a density gradient magnitude. So these are very important. The other thing, as I kind of alluded to, is this puffing frequency. So as you saw in the previous slides, there's some characteristic oscillatory pattern. Many studies look at this, like the frequency of these oscillations. And you can, it's very easy to do because experimentally you just inject helium and you can get some sort of frequency just by measuring pressure or velocity. Simulations, we can do this very easily as well. But previously, one of the founding works for this measured the puffing frequency in terms of the Struhel number and plotted it against Richardson number.
We have,
down here.
You've got 10 minutes till the end of the Q&A section.
Sounds good, thanks. And then on the, so puffing frequency in terms of Struhel number is very well correlated with Richardson number, but there's a change in scaling at higher Richardson numbers. And through our simulations where we are varying the Reynolds number, we actually see some deviations with the scaling, with the proposed scaling as well. And so right now we're investigating this, and this is so easy because we actually, with like even with the AMR and stuff, we just use ds.r method with YT. We get a probe, we just get the streamwise velocity, FFT it, max, done. That's it. And that's all we're plotting, plus some non-dimensionalization. And so we see something similar with Reynolds number, and we're focusing right now on understanding how the Reynolds number plays a role in connecting this with Satigan's results in 1996. Last two things I'm going to talk about, is I alluded to, is fluxes. So flux, just an integral over a cross-sectional plane. So if I were just to take a cut here, find like the mass flux through this plane, you can do this very easily with YT. You just add the field, sum over the two spanwise directions, and you get your flux. And these provide a basis for much of the theoretical prediction that is done in the community. In YT, this is very easy. As everyone knows, I don't think I need to talk about this too much, but the main result actually is the fact that all of these things, or many of these fluxes, I'm just showing mass flux here for simplicity, it scale approximately linearly. So they're just approximately straight lines. And this is completely new data that is being analyzed as far as the near field near these buoyant plumes. And this is really important because if we know that these fluxes scale linearly, then we can back out some velocity fields, density fields, et cetera, and help with some theoretical modeling. And actually, what I'm finishing up right now is showing that these types of relationships can be derived straight from the governing equations with some assumptions. The last thing that we're looking at is vortex dynamics. So the vortices that are forming here obviously play a dominant role in the dynamics. And so you can get a vorticity transport equation just by taking the curl of the momentum equation. Just for today, I'm going to be talking about this term specifically. So if you take this term, you contract the equation with vorticity vector. You can decompose this term into pressure that is due to a hydrostatic condition and a mechanical condition, which we're calling a gravitational torque and a baroclinic torque. So computationally, we do this with YT. We just add some derivative terms, and boom, you get your gravitational and baroclinic torque. And so for the first time, what we're showing here is, for this laminar case, is the baroclinic torque and the gravitational torque are of approximately the same order. Like the color axes I fixed to be on the same scale here. They're of the same order, but gravitational torque is predominantly positive, meaning that it contributes to adding vorticity to the flow, while baroclinic torque is positive and negative oscillating in the flow, and it's not contributing as much. And I have some other data on here. I'm just highlighting some of the findings. So some conclusions of future work. I mean, YT provides a much easier way to analyze the data. And this is done through visualization, frequency analyses, derivative integral fields that we can easily create with ds.add field. There's a lot of things that I would really like to include in YT if there were, 30 hours in the day. Like if we were able to do some higher order interpolation and derivative methods to get, second order derivatives. Or the other thing that I would like to do is embed in time series analysis. So taking averages of a statistically stationary flow would be something that I would really like to include into the YT database. That would make, I mean, at least what I do much easier, and maybe other people that are doing similar things to me may find this extremely helpful as well. And the last thing is actually our lab group does a ton of advanced time series analysis. So we do modal decompositions like proper orthogonal decomposition, dynamic mode decomposition, and we also do Lagrangian tracking. But we do this like on raw binary because my advisor likes Fortran, and that's generally what we do. And so, in order for us to do that nowadays with these new simulations with AMR, I basically have to output uniform binary fields. And it would be nice to just like not have to have that intermediary step to getting the data that I want. So with that, thanks for listening, and thank you for my funding from NSF and the rest of my lab at the Tesla and CU. Thanks.
Wow, thank you, Mike. That was really, really interesting and enlightening.
Thanks.
We have got a couple minutes for questions.
Okay.
Would anybody like to ask any questions of Mike? And remember to use the raise hand. Oh, I saw a hand go up briefly and then go back down. Don't be shy. Yes, Corentin.
Yeah, can you just go back to the to your previous slide? I didn't have
Oh,
time to
this one?
read everything. Yeah. No
Yeah,
worries.
sorry. Yep.
I was wondering whether part of it was not already done to some extent somehow.
What's that?
No, I'm just reading. Sorry.
Oh, sorry.
What is it that you call modal decompositions?
Yeah, so modal decompositions, they're basically a fancy statistical method of extracting data. And so usually like modal decompositions you perform on a data set to extract some sort of like coherent structure. And so as some of the videos showed, there's this coherent vortex shedding that happens in these flows. And so you can extract this data by forming some basis functions. So POD basically forms a set of basis functions that are optimal in capturing energy or I guess you would call it variance of the flow. And then you can use these to build reduced order models or just understand more fundamentally what's going on in the flow. If that kind of makes sense. It's hard. It's a little bit easier if I had a slide showing it, but I don't have one prepared. Sorry.
No, that's interesting.
Thank you. So in the interest of moving on, I'm going to ask Ryan to ask his question. And if we have time, we'll come to Cameron.
All right, so I'll make it really quick. Thanks for the talk, Mike. I actually used to work in a somewhat related field in undergrad, so it's always kind of cool to hear people talking about buoyant plumes.
Cool.
So regarding the Lagrangian tracking, is that something where you're saying you basically inject particles or you track them just during the post-processing, or do you have particles already in your simulations and you do some analysis on them?
Yep. So Amrex provides some what we call live tracking, essentially, where during the simulation you track the particles. What we almost exclusively do, though, is as a post-processing step, we seed the flow with some infinitesimally small particles, so they're massless, and just track the flow properties along as one of these infinitesimal parcels flows through the flow field. And so we generally do that with very, very turbulent flows, like very high speed turbulent combustion. But it's almost exclusively we do as a post-processing step for the moment.
Okay. Cool. It seems like AmRx is a really nice tool. So cool.
Yeah, no, they provide a lot of useful functionalities.
So I think we have time for Cameron, if you've got a quick question.
Sure. I hate to be a one-trick pony with this question because I just asked this similarly to Stephanie, but I think I'm actually really interested in the answer, and that is, do you find that the resolution that you're able to achieve has a dramatic impact on the behavior of these like buoyant turbulent flows? Because it seems like it would, but and I realize you're doing like 128 cubed over 1 meter, but turbulence goes all the way down. So
we have done a ton of convergence testing for this, and so first and second order moments like means and standard deviations of any of like the primitive variables don't vary much. As we get to higher order moments, derivative fields, you're kind of very much in a gray area as far as figuring out whether or not like what you're uncovering is physical or just a numerical artifact that needs to be sufficiently resolved. The fluxes so what I'm working on now is those fluxes and then doing some azimuthal averaging of just flow variables. And so far we found that with our resolutions, they are sufficient to resolve these. Adding another level of AMR, changing the AMR criteria doesn't change the results very much, so which is encouraging.
I see. Okay. Interesting.
All right. So I think we should move on to our next talk by Ryan Farber.